Bismillahirrahmanirrahim. In this video, we are going to discuss an example related to uniform PWM or the symmetrical PWM for the single phase full bridge inverter. As we already know that in the uniform PWM, we generate the gate pulses by comparison of a reference and a carrier, and that carrier is usually the triangular waveform as shown in front of you in this diagram that you can see the triangular waveform, and it is compared with the rectangular waveform to generate the gate pulses, and all of these gate pulses will be equal in the it will be equal in terms of width, and their width will vary equally because if we increase the magnitude of the reference, if we move the reference above, the width of all these pulses will increase equally, right? So in the uniform PWM, the width of all the pulses are equal, and the number of pulses in one reference cycle, that is the rectangular waveform over here, is equal to the frequency modulation index, that is equal to 6 in this case. So there will be 6 pulses in one cycle of the output, that is one cycle of the rectangular waveform. So you can see 6 pulses over here, right? And we have set the carrier waveform in such a way that this pulse is centered at this point. All of these pulses, the first pulse is centered at this point, second pulse is centered at this point, third pulse is centered at this point, and so on, fourth, fifth, and sixth. Okay, so what will be the time period in terms of angle of one cycle of the triangular waveform? That can be calculated with the help of this expression, that Ts is equal to T, where T is the time period of the reference waveform, MF is the number of pulses per cycle of the reference. So 6 pulses are there in one reference cycle, and the total time period in terms of angle is 2 pi. So pi by 3 is the switching interval in terms of angle. Okay, and each pulse will be centered at the center of that time period. So if I mark that point over here, this is the interval for one pulse, and that is equal to pi by 3. Sorry, this is the switching interval, not the interval of the pulse. The pulse will be centered at that interval, and that center point for this first one is pi by 6. Okay, similarly, if we look at the second switching interval, that will also be of width pi by 3, and this is centered at pi by 2. And similarly, the third pulse, that will be of width pi by 3, and this will be centered at this point, and the point value can be calculated as 5 pi by 6. Okay, so these are the center points. Similarly, if you look at the center point over here, this will be equal to 7 pi by 6. Center point over here will be either 3 pi by 2 or 9 pi by 6, and center point of this pulse will be equal to 11 pi by 6. Okay, now we are going to calculate the starting angle of all of these pulses. Let me call that this angle is let's suppose alpha 1, because this is the first edge, and then the second edge is this one. This is, let's suppose, at angle alpha 2, and this edge, this is at angle alpha 3, and this edge is, let's suppose, this is angle alpha 4, and for this pulse, let's suppose that this angle is alpha 5, and the ending angle of this one is alpha 6. Okay, so how we calculate these angles? First of all, we need to know the width of the pulse. So that we have already discussed in the previous video, that in terms of angle, the width of the pulse is modulation index times the switching interval in terms of angle. So modulation index in our case is this 0.5. So 0.5 multiplied by pi by 3. So that is equal to pi by 6. So width of the pulse in terms of angle is pi by 6. So it means this pulse width, that is pi by 6, or in terms of degrees, it is a 30 degree. We have already discussed in the previous video that we can calculate the starting angle of the pulse with the help of this expression, where m is equal to 1, 3, 5 or 7. That's an odd number. That should be less than 2p, where p is the number of pulses in half cycle. Okay, and the ending angle of the pulse is calculated with the help of this expression, where m is equal to 246. That's an even number up to 2p, where p is the number of pulses per half cycle. So ending angle can be calculated with the help of this expression, and the starting angle can be calculated with the help of this expression, where all of these 1 ts by 2 are considered in terms of angle. Okay, and then the Fourier series representation can be obtained with the help of this expression that we have already derived in one of our previous video. Okay, now we are going to perform calculations. We are going to find out the starting and ending angle of all of these pulses. Okay, so first of all, considering the first pulse, so alpha 1 will be calculated, and that can be calculated using the equation m minus capital M into Ts by 2, and m in this case is equal to 1 because we are calculating the rising edge. So it will be equal to 1 minus 0.5 into pi by 6. So this comes out to be pi by 12. So this angle will be pi by 12. Okay, so in terms of degrees, it is equal to 15 degree. Now let's calculate the alpha 2, that is the falling edge of the first pulse. So that can be calculated in two ways, either using this equation you can find out this angle, or you can simply add the pulse width in the starting angle to get the angle of the falling edge or the ending edge of that pulse. Okay, so I am going to add the pulse width in the starting angle. So pi by 12 plus del, where del is the pulse width. So this can be written as pi by 12 plus pi by 6. So this is going to be pi by 4, and in terms of degrees it is 45 degree. So this is the point pi by 4, right? That is the ending edge of that one, and you can see the difference of these two is the 30 degree, that is equal to the pulse width. Okay, so this difference is of 30 degree, and this pulse is centered at pi by 6, means 30 degree. So starting from 15 degree to 45 degree, this is the pulse. The starting point is 15 degree, ending point is 45 degree, and the center of the pulse is at 30 degree for the first pulse. Now considering the second pulse, this one, I am going to calculate alpha 3 and alpha 4. So alpha 3 can be calculated using the equation m minus capital M into Ts by 2. So m is equal to 3 and capital M is 0.5, and the Ts by 2 is pi by 6. So this is equal to 5 pi by 12, and in terms of degrees it is 75. And if I calculate alpha 4 using the second equation, so we will get that will equal to 105, or the other way around is that in the starting edge I am going to add the pulse width to get the ending edge. So 5 pi by 12 plus pi by 6, that is the width of the pulse. So I am going to get 7 pi by 12. So that is equal to 105 degree. So again you can see the difference of these two is 30 degree, and this pulse is centered at 90 degree, and that you can observe in this pulse that this is centered at pi by 2. The starting point, this one, let me choose a different color for this one. Let's suppose this is the starting point. So this starting point is 5 pi by 12, and this is the ending point, and this is 7 pi by 12, and this is centered at pi by 2. Okay, now let's move toward the third pulse, and the third pulse is this one, which is centered at 5 pi by 6. Now let's calculate its starting and ending angle. So that is alpha 5 and alpha 6. So if I calculate alpha 5, so alpha 5 will be equal to 5 minus 0.5 into pi by 6. So that comes out to be 3 pi by 4, that is equivalent to 135 degree, and alpha 6 will be equal to 3 pi by 4 plus del, and that del is equal to pi by 6. So 3 pi by 4 plus pi by 6, I am going to get 11 pi by 12, and that is equal to 165 degree. So the difference of these two is 30 degree, and this pulse is centered at 150 degree. So centered at 150 degree, right? So we have calculated the angle for the angles for the third pulse. The starting angle is 3 pi by 4. So this angle is 3 pi by 4, and this angle is 11 pi by 12. Similarly, we can calculate all of these angles. This angle can be calculated, this angle can be calculated. Similarly, the angle of this edge and this edge can be calculated, and so on, by using these equations which are in front of you. These angle can also be calculated using another expression that we have also discussed in one of our previous video, that instead of using the edge number we can use the pulse number, and for that our equation will be like that the starting angle alpha m, the starting angle will be calculated as 2p minus 1 minus m into ts by 2, where p is the pulse number, right? And over here, this is our first pulse, this is our second pulse, this is our third pulse, this is fourth pulse, fifth pulse, and sixth pulse. So either you can use these equations, or you can use this equation to find out the starting angle of the pulse, or ending angle is calculated with the help of this expression, that is 2p minus 1 plus m into ts by 2, where again p is the pulse number in the output waveform. Okay, so after calculating these angles, now we can write down the Fourier expression for our output voltage waveform, that is this one. For this we were requiring the first of all the pulse width, that is over here, and the starting angle of the pulse. So if we get these two information, these two values, and the supply voltage level, we can find out the content of any harmonic that is present in this waveform. Okay, so now let's take this expression, the Fourier series expression, and then we simplify that one. So Bn is given as m is equal to 1 to p, where this is representing the number of pulses, pulse pair, right? So this small p is indicating the number of pulses per half cycle. So 4 Vs by n pi into sine of n del by 2, where del is the width of the pulse, into sine n alpha m starting angle of the pulse plus del by 2, that's the width of the pulse. Okay, so in this case our small p is equal to 3 because we have 3 pulses in the half cycle. So 3 pulses per half cycle. Okay, now let's take m is equal to 1. So we are going to calculate Bm1. So that will be equal to 4 Vs by n pi into sine n del by 2. Okay, what is del? Del is the width of the pulse. So width of the pulse is pi by 6. So dividing it by 2, we will get sine n pi by 12. Okay, then sine n, the starting angle of the pulse, that is pi by 12 plus the width of the pulse divided by 2. So that is sine, again pi by 12. Okay, so this can be written as 4 Vs by n pi into sine n pi by 12 into sine n pi by 6. Now let's calculate it for the second pulse pair by taking m is equal to 2 in the expression over here, A. So Bm2 will be equal to 4 Vs by n pi into sine n pi by 12, because the width of the pulse is same, into sine n alpha m. Now alpha m of the second pulse, that is equal to 5 pi by 12, that is the starting angle of the second pulse. So that is alpha 3 over here. So 5 pi by 12 plus the width of the pulse divided by 2, so that is same as above. So pi by 12, so this can be written as 4 Vs by n pi into sine n pi by 12 into sine n pi by 2. Now let's repeat the same thing for the third pulse pair. So Bm3 will be equal to 4 Vs by n pi into sine n pi by 12 into sine n starting angle of the third pulse, and that is equal to 3 pi by 4 plus the half of the pulse width, so that is equal to pi by 12. So this can be written as 4 Vs by n pi into sine of n pi by 12 into sine of 5 pi by 6. Now the summation of all of these is equal to Bn. So Bn can now be written as Bn is equal to Bm1 plus Bm2 plus Bm3. So if we sum them together, so from this expression we will get the Fourier series coefficient Bn for this waveform that is shown over here in this diagram. This is the waveform for the output voltage of the inverter. So output voltage of inverter, that is this one. Okay, so now let's sum all of these together. So Bn now can be written as Bn is equal to 4 Vs by n pi into sine n pi by 12, that is common in all of these terms. So inside the bracket we can write sine n pi by 6 plus sine n pi by 2 plus sine, there is n over here as well, so sine n 5 pi by 6. So this is the Fourier series expression for 3 pulses per half cycle, right? So now by using the value of n, you can find out the content of the different harmonics which are present. So if we take n is equal to 1, we can find out the fundamental component of the output voltage. So if we take n is equal to 1 over here and we solve it by taking Vs is equal to 120 volt, if our DC supply is 120 volt, so our Bn will be equal to 79.0893. So that is B1. So I should write it, I should write it B1, right? So our fundamental output voltage or V01, so that is equal to B1 into sine of omega t. So 79.0893 into sine of omega t, this is our fundamental component. Okay, now if I take n is equal to 3 and Vs is equal to 120 in this expression, this one, this is the expression for the Fourier series coefficient Bn, and as we know this one, we can say our output voltage V0, that is the summation of Bn into sine of n omega t, where n is an odd number up to infinity. Okay, so we have taken we have calculated the fundamental component. Now the third harmonic, second harmonic will be 0 because this expression is only valid for the odd harmonic. So if we calculate B3 now, and how to calculate B3? By taking n is equal to 3 in this expression. So if we take n is equal to 3 and simplify this one, this is going to give us 36.0127. So our third harmonic component V03, that will be equal to B3 into sine of 3 omega t, right? So from here I can write that it is 36.0127 into sine of 3 omega t. This is the third harmonic component which is present in the inverter output. And similarly, if we calculate for the other harmonics, fifth harmonic, seventh harmonic, so we can evaluate the harmonics. So let's suppose n is equal to 5 now, Vs is equal to 120, so B5 will come out to be 59.0330. So V05 can be written as 59.0330 into sine of 5 omega t, and so on, right? So you can now evaluate the magnitude of the any harmonic which is present in the output voltage waveform of the inverter. So I'm just going to quickly write down for the seventh harmonic. For seventh harmonic, basically Bn comes out to be negative, but as we are going to express it in terms of that, so B7 in terms of magnitude it will be equal to 42.1665. its actual value is negative. Okay, so that can be reflected in the phase of that harmonic because of having the negative sign. Similarly, if we take the ninth harmonic, so B9 will be equal to 12.0042 and so on. So all of the harmonics now can be calculated. Okay, so once you calculate all of these, you can find out the fundamental component, you can find out the third harmonic and so on, and then you can calculate the THD in the waveform, in the voltage waveform, with the help of this expression, that THD in the voltage waveform, that is equal to V total RMS, V RMS value of the signal, the square of that one, minus the fundamental component square divided by the fundamental component. Okay, so you will get the THD in the voltage waveform. Okay, so what we have done in this example, we have seen how we can calculate the angles of the pulses, and then with the information of those angles, how we can represent our inverter output voltage in terms of Fourier series, and then we have seen how we can calculate the harmonics, different harmonics which are present in the inverter output voltage waveform, and with that information we can calculate the THD of the voltage waveform. So you can use this example to find out the spectrum of the sine PWM. In the sine PWM, this rectangular waveform will be replaced with the sinusoidal waveform. Okay, so you can write down a computer program to find out all of these angles, and then you can evaluate the Fourier spectrum easily. I will share the MATLAB file for the uniform PWM, which you can use for different MF, for different modulation index, to evaluate all the angles and the spectrum of the uniform PWM voltage waveform. Thank you.